All right, just as everybody starts to roll in, um, I'm just going to introduce myself and what we're doing today. I'm here. My name is Reese with Chegg, presenting computer science office hours. These are virtual office hours, so you can just think of them as regular office hours, though. You ask questions just like you usually would, and I'll answer them. And here are the topics that I'll be going through today. I'll be going through some Boolean algebra, logic gates, truth tables, and Karnaugh maps. And if you have any questions about anything else, I can switch gears and we can go on and introduce different topics. Or if you want me to cover more practice problems of one topic, just make sure to drop that in the chat and I'll do that as well. So I'm going to get started just as people roll in. And again, if you have any questions, just make sure to drop those in the chat. So just to start off, I'm going to be getting into some simplifying Boolean expressions. So for number one, it's A or not A and B. And if you're a little bit unfamiliar or just getting into Boolean expressions, just as a quick reminder, a plus sign is an or. So plus is an or. Multiply is and this means not, just as a quick refresher. So if we start out with A or not A and B, we're going to first just think about like what A and or not A means. So A or not A will always be true, no matter what. So we know that A will either be A or not A. And because of that, we need either B to be true or A to be true. Because if A is true, then we know, if A is not true, if A is not true, then we hit this. And if B is true, we need it to be true in order to hit this, not A and B. But if not A is false, then we know A is true. So that will always work. Um, and just as more people roll in, we're doing computer science virtual office hours hosted by Chegg. I'm going over some Boolean expressions, and here are the other topics I'll be going over, some logic gates, truth tables, and K-maps. If you're interested in any of these digital logic introduction concepts, make sure to stay tuned and follow along with me. If you want me to go into any other computer science topics, make sure to drop those in the chat as well. And as always, if you have any questions, make sure to drop those in the chat and I can elaborate on what I'm doing. And if you want me to do more practice problems of a certain subject, also just make sure to drop those in the chat. And if you have any questions about any other topics, make sure to scan the Chegg QR code and you can see our live office hour schedule at the same times every week. Okay, so this simplified will be B or A. And then moving on to the next one, just gonna move this over here. Oh no, it got caught. Just erase it. And if you guys want to watch back anything that I did, if anything wasn't clear and you want to see it again, these will always be recorded and posted on Chegg YouTube under the live section if you want to just look and rewatch anything or just practice it again. So the second one is A or B and A or not B. So if we distribute this, it's just normal distributive property, just like you learned in math. So A and A is just A. A, sorry, sometimes when my mouse gets in there, it gets confused, so I always have to make sure to put my mouse out of there. Um, A, and then we'll add not B and A, and then we'll do B, so A, B, and then not B and B. So not B and B will always be false, so that will always be 0. So we don't care about that. We can eliminate that from our simplification because we always know that's gonna be false. B can either be 1 or it can be 0, but it cannot be both. And then if we simplify this a little bit more, we can either have A or not B and A, or A and B. And you can see in all of these, A is essential, so we can just simplify this to being A. Because if A is true, we already know that it's gonna simplify, to be true. And we also know that either this or this will be true, so we know that at least 2 of these will evaluate to true. So we know that this is gonna be true only if A is true. If and only if. If you guys are in, if you guys are in any discrete math courses, like that, you know, if and only if and proofs is really important. So the third problem I'm gonna get into is A and B or C, and not A and C. And if you're just joining, this is Computer Science Office Hours hosted by Chegg, and my name is Reese. And right now we're simplifying some Boolean expressions, and we're gonna get into more like introductory to digital logic concepts later. But if you have any other computer science topics that you want me to go over, just make sure to drop those in the chat and I'll switch gears a little bit or plan them in. And if you have any questions about anything I'm doing, just make sure to drop them in the chat and I can explain a little bit more. Or, really important, if you see me make a mistake, really make sure to tell me in the chat because it's really easy to make mistakes and you have to double check my work. Okay, so back to the problem at hand. If I distribute A here, that will give us AB or AC or not A and C. So this we can simplify to C and A or not A, which we can just say is C because A or not A will always be true. So our equation will then simplify to A and B or C. And that's it. A and B or C. Now, I hope that made sense. If you have any questions about any of those simplifications, just make sure to let me know. And as we get into our next problem, if anyone's rolling in, my name's Reese, and these are Computer Science Office Hours hosted by Chegg, and these are just some virtual live office hours, so if you have any computer science questions or topics that you're having trouble on in your classes, just drop those in the chat and we can go over them. So here we're given a Boolean function, and the first part is to draw a truth table. So I'm gonna go and make columns for A and B and F. Okay. Oh, and C. Oops. So a question from TikTok is what grade level is this? This covers all lower division college courses for people in their first or second year of computer science or getting a computer science minor, or if you're just a self-taught programmer and just want to understand some concepts better. But any level of computer science that you're in college or just teaching yourself, this covers. So if you have any topics that you want me to cover that's not digital logic, we can switch gears a little bit. Okay, so F will be true if A and B are true, or if B is false and C is true. So I'm just gonna draw out all our possible values. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Oh, I'm gonna have to move this. Just move that up there. Okay. And then 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, I think that's all the combinations, but yeah, that should be it. Okay, so if they're all false, F is going to be false. If C is true and A and B are false, F will be true because not A or not B and C will be satisfied. If A is false, B is true, and C is false, F will be false. And then this will be false. So will this. That will be true. That will be true, and that will be true. Okay. If I was wrong about any of these, please let me know in the chat. I always make mistakes, and it's really easy to, especially with all these binary numbers. So please double check me, and just work along with me if you want to. Okay, so that's our truth table. And then the circuit diagram, it's gonna be, if we have 4 inputs or 3 inputs, we have A here, B, and C. We want to AND A and B, and we want to AND not B and C. So I'm gonna move C down a little bit, and then we can add in a NOT gate, which looks like that, and then add another AND gate, and then we can connect those. I need a little bit more space. Connect those to an OR gate, and that will output F. So that gives us A and B, or not B and C. Another good question from TikTok, this office hours covers like all computer science, like first or second year topics. So like if you're in your second year, you're getting into like more advanced stuff. This topic in particular, it's covered, it depends on what you're taking. It's covered somewhat in some like lower division classes and like further and upper division classes. But these office hours overall are meant to be like for all introductory or first and second year courses. So if you have other topics, I can switch gears and cover those if this is too advanced. Yeah, there are just so many topics to that computer science envelops in your first and second years that you might not have gotten to this yet, but it's usually covered in like discrete math, or intro to systems, or like a intro to architecture class, something like that. Okay. For this function, I'm gonna do sort of the same thing, but I'm gonna pause here for 1 second for more people who are just joining in our first 15 minutes. My name is Reese, and I'm hosting computer science office hours with Chegg. And you can think of this as like normal office hours, you know, it's virtual, it's live, but you like can always ask questions, you can follow along, and the topics I'm covering right now are Boolean logic and getting into some circuits and circuit diagrams and K-maps. But if you have other questions that you're struggling with in some of your computer science classes or things that you're struggling with, like in self-taught programming, feel free to ask those and we can switch gears. These are super flexible and meant to work around anyone who joins. So don't be shy to ask questions or request different topics. And these will happen at 6:15 every week Pacific time. So if I don't get to something now that you want me to cover next time, be sure to request that, and I will make sure to provide practice problems for that. And if you have any other trouble with any other topics, just make sure to scan that QR code, and those are all the Chegg live office hours that we have throughout the week, every week. So this function is A or not B, and B or not C. So I'm going to make a truth table. And the cool thing about K-maps is we can have a function, right? And I simplified some Boolean logic functions before in my first problem, but those were through like properties of Boolean logic. With K-maps, you don't need to remember all those properties. K-maps are like super easy to just identify some simple simplification. Okay, 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. All right. So for all of these being false, that will be 0. This will be 1. That will be 0. 0 0 1 1 1. Okay. Yeah, and how I got this is I checked to see. Actually, I'm gonna add it to the truth table because I'm sort of doing it in my head, but also I make mistakes super easily. So it helps to just put the expressions here. So these both have to be true for F to be true. So here, oh no. I move my mouse out of the way again. So here this is true, but this is false. So F is false. This is true and this is true. So F is true. This is false and this is true, but they both have to be true. This is false. This is true. And this is true, but this is false. I'm on this one also. My line's got a little bit messed up. This is true. This is true. This is true because A is true. And this is true because B is true. And those are both true. Okay. So that just kind of breaks it down how I go through it. And only the rows where both ones are true will F be true because it's an AND function. Okay. But now we have that. I'm going to make a K-map. So I'm going to add a new page. We ran out of space. All right. So K-maps, if you remember from your classes, you have one letter and then you have two other letters. But if you had 4 letters, you would do like A, B on one on the rows and C, D on the columns. But you have rows and columns. So A can either be 0 or 1. And B and C can be both false, C true, they're both true, or only B is true. And the reason I put them out of order like this is, if you remember, only one bit can switch at a time as we move from columns and down rows. So if I put 1 0 there, then it wouldn't work if we switch these two. That would not work because 2 bits would have to flip from 0 to 1 to 1 to 0. Okay. So now if I fill this in, I'm gonna have to look back up here a little bit. So if they're all zeros, false. If only C is true, that's true. If B and C are true, false. and then 101 is true, 100, and the rest of these are true. Okay. So K-maps, you make rectangles, and you do shapes. So I'm gonna identify a couple things that I see. So this is one, um, and this is one. This is also one, but that's kind of redundant because it's covered by the other two. So you wanna make as few shapes as you possibly can, and that will help you simplify it. So this rectangle, for example, we want to identify the bit that stays the same between them, and we can see that it's C. So we know that when C is true and B is false, that's another way to write not. When B is false and C is true, then F is true. And then this rectangle here is when A is true and B is true. Okay, so that's our simplified function using a K-map. And this was our original function. This is our simplified one. Okay. Moving on, here you start with the truth table. Um, if anyone's just joining now, these are computer science hours hosted by Chegg. My name is Reese, and we're going through some of like the toughest like Boolean logic things in your intro classes that you might run into. If you have any questions about anything other than like Boolean logic, K-maps, and like truth tables, then just put that in the chat. I can switch gears. It's super flexible. It just depends on what people are interested in. And if you want to follow along, that would be great. If you want to review what we've gone through, then you can always review this. It's always posted on YouTube, recorded on the Chegg YouTube. And if you want more than just live help, Chegg.com offers 24/7 help for computer science for any of your subjects. And if you want live help for any of your other subjects, scan the QR code and you can look at the schedule of our office hours throughout the week that are the same times every week, so you can come back. Um, so I believe someone from TikTok is asking about, Karnaugh maps, and that's what we just went over. If you want more practice problems about Karnaugh maps, I can add more practice problems. I don't think I have any prepared for right now, but I can do one with this problem if that would be good. So just let me know in the chat if you want me to do more K-map practice problems. And then, someone else is asking about computer architecture. So this is like sort of intro to computer architecture. If there's anything specific you want to know about computer architecture, um, just drop that in the chat. But we're drawing some circuits, which is like combinational logic for computer architecture. But if there are other computer architecture problems or topics you want me to go into, just drop those in the chat too. Like sequential logic is usually like the step after combinational logic. Okay, so I'm given this truth table, and it's we're asked to write the expression for f in SOP and POS forms. And if you forgot what those mean, SOP means sorry, I'm a little sick. Sum of products, and POS, oh, that's a B. POS means product of sums. Okay. And SOP is you can think of it just as like you want to see which ones are evaluate to true. So F equals 1 you want to focus on, and product of sums you want to focus on the ones where F equals 0. Um, so we can go about how to do that. First, we'll do sum of products. So everywhere where f evaluates to true, I'm just gonna highlight that here. So it's a lot. Um, so we know that if A is false, B is false, and C and F are true, then it'll evaluate to 1, or A false, B true, C false. Oh, wait, sorry. I'm doing F also. Oops. There. So it's just 3 variables. My bad. Or A is false, B is true, C is false, or A is 0, B and C are 1, or A is 1, B is 0, and C is true, and A, B are true, C is false, and or A, B, and C are true. So I hope that makes sense. If it doesn't, just let me know. But how I think about it is if any of these have these exact values, like if A is 0 and B is 0 and C is 1, then we know that F will be 1. So what we're doing is we're listing out all the conditions where F will be 1, like F will be true, and putting that as like an or statement or a sum. Okay, so that's our sum of products, and then I'm gonna do the same thing with product of sums, but this will be shorter because we only have 2 cases where F is false. And this one's a little bit less intuitive. I find sum of products super intuitive because, I find yeah, because you can just see, like, if these conditions are true, then F will be true, or if these are true, then F will be true. But product of sums is written like F equals oh, and it's always F equals, so this equals F. A or B or C, so we invert them. So because that's not A, we invert it to be A. And not A or B or C. Um, and if that's, like, a little bit confusing about why that would be true, we can just look here, right? Like, in this case of false, they're all not right, but so this would evaluate to 0, so therefore it would be false, and this would evaluate to 1, but 0 and 1 is 0. But all the other ones, at least 1 from each category evaluates as true. So that way, this is another way to represent F, and product of sums in this case is a lot shorter just because there are less cases where F is 0 than F is 1. So I think someone's asking about some classes that or some questions that relate a little bit more to econ, I believe. So we have Intro to Economics office hours, I think, um, on Chegg. So if you just wanna scan that QR code, you can see the schedule of all the different subjects we offer and the times that we have them. And so this class is computer science. We're covering pretty much like any topic that you'd see in any intro course that you encounter in your first or second years. Anyone who's getting a computer science minor will see all of these topics. Or anyone who's a self-taught programmer who wants to go just like into anything seen in any introductory course, like this would be for you. And this is hosted every Tuesday at 6:15 Pacific time. So if you have topics that you want me to cover next time, just drop those in the chat and I will make sure to prepare problems that goes deeper into that. So finishing up that, we have our second question, and that's just to simplify the expression. So I'm going to simplify it from product of sums because that's a lot easier. And first I'm going to distribute. So distribute all that. So A and not A, or AB or AC, and then distribute this one, so not A, B, or BB, or BC, and then the last one is C, so not A and C, or B and C, or CC. And then just some, like, easy simplification. We know that this is 0, so sorry, we know that this is 1. No, we do know that it's 0, my bad. Because A and not A can never be true. That will always be 0. So that gives us AB or AC or not AB, and then we can just rewrite this as B or BC or not AC or BC or C, and rewrite that as C as well. Okay, so that's like a lot we've got going on. I'm just gonna make a new page. So what I start doing then is I start like bringing terms out. So like C, for example, if we bring that out, any term that has a C in it. So C is AC or not AC or BC or 1, right? Because C times 1 is C. And so because this is 1, right, we don't need any of these terms because if C is true, this will always evaluate to true, as we can see here. So we can rewrite this as C or AB or not A and B or B or BC. Okay, and then kind of the same thing, right? We can see the term B is in here, and I won't rewrite it, but because the term B is in there, we can just rewrite this as C and B, because all these other terms also have a B. So if B is true, those will all it doesn't matter if those are true or not. If A, not A, or C are true, it will already be true. So we simplified the expression as C or B. Yeah, and we can see in our expressions, like, that covers all the cases, like, if B is true or C is true, then F is true. And we can see that here as well. So this is C, B, BC, C, B, and BC. Yeah, so all we need is either B to be true or C to be true. Okay, moving on. And if anyone's just joining, we're about halfway through computer science office hours hosted by Chegg. My name's Reese. And if you have any computer science questions, just drop those in the chat if there's any topics you want to cover. Right now we're doing like intro to computer architecture, like digital logic and Boolean algebra, and we're doing some K-maps and truth tables. So if you're learning those in your classes and want to just do some practice problems and follow along, you're free to do that. And if you have any questions or any different topics you want me to cover, also just drop those in the chat and I can switch gears. Okay, so if you're taking these classes, you've probably heard that NAND and NOR gates are your universal gates. And what that means is that NAND and NOR can be used to make up any other gate. So we're going to prove that right now. So we're going to use not A with NAND. And I like to do a quick truth table with NAND. And I'm just going to use A. So, or I will use AB. And then we'll say A, NAND, B. Okay, 0, 0 would be 1. 1, 0 would be 1. 0, 1 would be 1, and 1, 1 would be 0. So the only case where not and evaluates to false is if A and B are 0. Okay. So for A, A can either be 1 or 0, right? So if A is 1, we want it to return 0, and if A is 0, we want it to return 1. So if we see here, right, if we NAND 0 and 0, it returns 1, and if we NAND 1 and 1, it returns 0. So we can just NAND A with itself to make a NOT. So those do the same thing, and this is how you draw a NAND gate, and that returns NOT A. Perfect. Okay. So for the second one, we want to return A and B. So A and B is the same thing as not A and B. So what we just learned how to make a NOT gate, right? So we can do a NAND again, and then we NAND that to make NOT. So we can do A and B and then we do that again to make A and B, right? Because this returns A, not and B, and that returns A and B if we NOT it. Okay, and the last one we're gonna do is A or B. Okay, so A or B, we want to return true if one or the other is true, right? So what we can do is this one's a little bit more tricky. So I'm gonna write it like this, right? And if you guys are taking these classes, you've probably heard of De Morgan's law. So I'm going to do 2 knots around A or B, and that's like double negation, right? So these 2 things are equivalent. And then using De Morgan's law, I'm gonna distribute the knot. So knot, and I'm gonna distribute it like that. And De Morgan's law teaches us that oh, sorry, that the little apostrophe is the not symbol if you're so there are 3 not symbols. There's this or this or this. Those all mean not A. Okay. So not A and not B is gonna be equivalent to A or B, and I can just prove that really fast by saying if A and B are 0, right? Not A and not B is gonna be 0, or is gonna be 1, sorry, and not that is 0. If A is 1 and B is 0, that's gonna evaluate to 0, and not that is 1. Same thing here. And then not A, not B ANDed together is gonna be 0, and not that is 1. So that proved that these 2 equations are equivalent. So this is already a NAND, right? So we do not A, NAND, not B, right? And we already learned how to make a NOT gate up here with a NAND gate. So what we can do is take A, we NAND it with itself, which does a NOT, and we do the same thing with B, and then we NAND those. And if anyone's kind of curious about the computer architecture aspect of why we even do this with universal gates, right? It was really cool for me to realize that it's so much cheaper for like computer architecture engineers to make a bunch of NAND gates, right? Than like try and predict what gates will be used, right? So if NAND gates are made over and over and over, or NOR gates, we know that we'll be able to make whatever we want. But if we make OR gates, right, then we won't be able to do all of the things we need to do, and we have to like mix and match, and that's a lot more expensive. So I just thought that was a cool fact when I learned it. And again, if anyone has any questions about anything that I just did or something else you want me to do, just let me know. But we're gonna move on to simplifying these functions. And someone asked about K-maps a little bit earlier. So instead of just using like distributive properties, I'm going to make K-maps for them. Or I'll start with just one of them and see if we have time for the rest. And this is my last problem, so if you want me to cover anything else in the next 20-ish minutes, you can do that. Otherwise, we'll keep covering these same sort of things. So first I'm gonna draw a truth table for the first function. Um, I'm gonna do it for each OR statement. C or AC and F. And then I'm also at the same time gonna do the K-map because I think that'll be a little bit easier and faster. So I'm gonna write all the possibilities of A, 0, 1, and then B will be 0, 0, 0, 1, 1, 1, and 1, 0. Then I'll just fill that in. All right. So 0, 0, 0, this is 0, this is 0, and this is 0, so F is 0. So I say 0 there. And then 0, 1, 0, 0, 1 is 1 here, and 0 here. So that's 1 because these are all ORed together, equals F. 1 there, and then 0, 1, 1, 0, 1, 0. So that'll also be a 1. 0, 1, 0 is 0, 0, and 0. So F is false there. And then 1, 0, 0 will be 0, 0, 0. 101 is 0, 0, 1. So F is true. 111 is going to be 1, 0, 1. So that's true. And then 110 will be that. All right. So we filled in that K-map. And K-maps, again, if you weren't here earlier, K-maps are so cool because I think it's a much easier way to simplify equations than remembering all the properties with Boolean logic and trying to do it, like, and trying each thing and figuring out if you're doing it right. Like, K-maps are just super easy comparatively. Okay, so I'm gonna erase this truth table. We don't really need it anymore, and we have our K-map. And so this rectangle really stands out to me as the biggest one, and that'll really help us simplify it. Or it's a square, my bad, not a rectangle. This is not geometry. And this rectangle will also help us fill in the last piece of it. Okay. So for this square right here, we want to see what this square will represent. So the one bit that stays the same throughout that is C. So we can say if C is true, we know that F's going to be true, or F1 will be true. And then the other case where F will be true is if A is 1 and B is 1. So, or A, B. And those are the only two cases where F1 will be true. Okay. If you guys have any questions about that, just let me know. If you want me to cover, again, any other topics in the last 15-ish minutes, also let me know. And if you want to go over anything I did, if I went too fast or anything, I can explain it a little bit slower if you want to review it. Just go on YouTube to Chegg, and these are all uploaded after and recorded, so you can go over the practice problems with me again. Okay, I'm gonna erase this though, so we can move on to F2. All right, and make a new table. Okay, this table is gonna be A or BC. So we can already just fill in all the places where A is true to be 1. I don't even need to use my truth table for that. Honestly, I don't think we even really need this. We can just evaluate it because this one's a lot more simple. And then the other cases, we need both B and C to be true for F2 to be true. Okay, so that creates our K-map. And I'm gonna do the same thing as last time, where I make the biggest rectangles or squares that I can. And that gives me those two. So this one is A, and this one is B and C. So that just gave us the same expression. So we already know that this one is already simplified. That's the most simplified that it can get. But we just double check that in case you're ever asked that on an exam, like simplify this further and like a multiple choices. Like it can't be simplified further. That's how you double check to make sure. Okay, I am gonna make a truth table for this because we have 2 and statements that I wanna do. Okay. So, and I'm gonna make this leftmost column A, B, C. All right, so for 0, 0, 0, everything is 0. And for 0, 0, 1, this is false, but this is true. But remember, we're anding them together, so they both need to be 1 for F to be true. So it's still 0. That's 0. And then 0, 1, 1, those are both 1, so F is 1. That's awesome. 0, 1, 0 is 1, and 0, not true. So 0. And then for A, we see here that both of these have A in them. So if A is true, both of these will be true, and therefore F will be true. And so we can just fill that in. And I kind of recognize this K-map. It looks a lot like the one we did before. And we can just double check that by seeing A here and B and C here. And look at that. It creates the same function, A or BC. Okay. Now, some of you might have noticed that I'm always doing product of sums sum of products. And that's just because like the ones and the trues are a little bit more intuitive to me. So like instinctually, I kind of just do that. But we can use K-maps the exact same way, but with product of sums instead, which is where we circle the zeros instead of the ones. So I'm gonna do that with these now, and I know I just erased all the K-maps, but I think I can get them all back. All right, so instead of focusing on the ones, I'm gonna focus on the zeros. So this is a circle, and it can wrap around also. So this is also gonna be a rectangle. All right, and then, oh, I erased that. We want that. C or AB. Okay, so for these two, this rectangle is going to represent when C is false. So again, we're doing product of sums, right? No, we're doing sum of products. So that means we're going to do the opposite. So if we see that C is false here, we just do C. And then the other case is when, oh, it's not just C. It's when C is false and when A is also false. So we do C and A, or this rectangle is when B is false and when A is false. So we do or BC. I did it again. I did product of sums again. See, it's so easy. I always want to do product of sums. So sum of products takes the form x plus y or y plus z or et cetera, et cetera, et cetera. So it's C or A and B or A. And if we distribute that, we would see that we get the exact same thing as we got before, which is A or BC. But the sum of products version is going to be this. So in your exams and stuff, you're probably going to be asked to put it in sum of product form or product of sum form, and just make sure to not get them mixed up like I do. But it's going to be the difference between locating all the f equals 0 boxes versus f equals 1 boxes. All right, now if I do this again for the other ones, since I already did the truth tables, I'm just going to fill this out really fast. Okay. And so this time we're going to circle, and I know they're the same equation, but we're just going to do it anyway. So I'm just going to circle these same two again. And since we already did it, we know that it's C plus A and B or A. All right. And then if I do the last one, okay. Again, I'm just going to fill this out. That'll be C. And it's easier because I'm just going to go off this instead. So anywhere where C is 1, I'm going to put a 1. And anywhere where A and B are 1, I'm also going to put a 1. So then the rest are zeros. And now since we're focusing on the zeros, to make sum of products, I'll do that. So this 0 can wrap all the way around. And now we'll look at the common factors in our two rectangles. So for this first one, that is when B and C are false. So in sum of products, we invert those. So we're going to do B is true or C is true. And then for our second rectangle, our common factors are A is false and C is false. So again, we're inverting that. So it's going to be A or C. And that's our sum of products for this first one. Okay. So now as we're wrapping up a little bit, I'm just going to go back and do kind of the same thing with the Karnaugh map before, and just go through and do like some sum of products ones just to show you that, because I mostly just showed you product of sums. And just as we're wrapping up, just make sure to drop anything in the chat that you want me to cover next week. I'm here from 6:15 to 7:15 Pacific time every Tuesday. I'll cover different computer science topics depending on what people want me to cover. But if you want anything specific for next week, just make sure to let me know. If you guys want any other subjects tutoring live, also, I'm sorry again, I am sick, so my bad. But if you want any other subjects to be tutored, in live office hours, just make sure to scan that QR code and you can see our schedule. If you want 24/7 like help with Chegg, just check out chegg.com, and also make sure to follow Chegg on all of their socials on Instagram, Twitch, TikTok, and YouTube, just to stay up to date with our office hours and any other help that we have. Okay, but I'm gonna go through and put this in sum of product form instead. I did that one. Okay, I didn't do this one. So here I circled the ones, right? And that made a product of sums equation. So instead, I'm going to do sum of products. So these ones here and these ones here are zeros. So then what we can do is for each circle, we figure out what variables they have in common. And we can see that when A is false and when B is true, that's when F will be false. So in our sum of products, we can write that as A or not B. And then the second one is going to be, let's see, these two. So not B and not C. So in our equation, we can write that as B or C because we invert them when writing sum of products. All right. Are there any other Karnaugh maps I did? There aren't. Okay. So with our last like 5-ish minutes, I'm just gonna go and just do like one more K-map problem for, let's see, those are already simplified. I'm gonna do it for this problem. So F is already given in product of sum form, and I'm gonna turn it into sum of product form using a K-map. And then we can also draw it, the circuit, as sum of products instead of product of sums. Oh my gosh, I've been saying it the opposite way. Down here, when it says sum of products, this is definitely product of sums because in the end, it's multiplied. So you can think of it logistically. I get it mixed up all the time because it's the same letters, but if it's product of sums, we know that it's getting multiplied at the end and summed first. And if it's sum of products, then we know it's getting added at the end and multiplied first. But it doesn't matter as long as you know that the way to write each equation and make sure that they're equivalent. Okay, so I'm just gonna do that here. So in my K-map, I'm just gonna have A and BC, so 0, 1, 0, 0, 0, 1, 1, 1, and 1, 0. Right, so this is 0, 1, this is 0, this is 0, this is 0, 1, 1, and 1, I think. Yeah, that will be 1. Okay, so instead of making circles with the 1s, I'm gonna make circles with the 0s, so here and here. And I think this is one that we just did, but let's just make sure we can do it again. All right, so here is going to be not A and B. So in our sum of products, that'll be A or B. I keep saying that. It's product of sums, and our product of sums. Product of sums. And this one, which is not A and not B. Or sorry, not B and not C. So that'll be B or C. And it's like super easy to know which is which. And this is a not. Because, you know, it's getting multiplied, so obviously it's a product of sums, but POS and SOP just sounds so similar. And then in our last minute, I can quickly just draw this circuit. So we OR A and not B. So we put B through this and we OR it, and then we OR C and B, and then we AND those together, and that will make F. Beautiful. So these circuits look super similar, but it's just the two ways to write it. It's just ORing it at the end versus ANDing it at the end. And this is product of sums, and this is sum of products. So the live's almost over, but if you guys enjoyed this, make sure to come back next week at 6:15. If you guys want to do any other live office hours, make sure to scan that QR code to see the schedule. I hope you had a good time. A big thanks for showing up, and I hope you guys have a good